All right. Hello, everyone, and good afternoon. Can you hear me?
Yeah, we can hear you, Professor.
Okay, thank you. And so let's continue from where we left on Monday. In the last lecture, right, we basically introducing the fundamental flow patterns for the uh, internal incompressible viscous flows. Okay. We're seeing that for the flow, internal viscous flow, if they flow into a pipe or between or for flow into a flat plate, the flow field, can be separated to two regions, right? The entrance region and fully developed region. In the fully developed region, basically the velocity profile of the flow will not change on the x direction. It's only a function of r. Okay, on the x direction, the velocity profile will not be changed. So that's why we call it fully developed. And also that based on the, the Reynolds number you calculated, that Reynolds number you calculated based on the diameter or, the spacing between the two plates. Based on that Reynolds number, you can also determine that whether or not the flow is laminar flow or turbulent flow. Okay. We have a critical Reynolds number for the flow inside a circular pipe, which is 2300. And if the flow is larger than that, it will be turbulent. If it's smaller than that, it's a laminar flow. And for the flow between parallel plates, we have another critical number. And we're starting the study for the flow between parallel plates. Okay, assuming that you have two plates. We do it for the two cases in the last lecture. Okay, the first case is that both plates are stationary. And the second case is that the top plate is moving and the bottom plate is stationary. Okay, and if in the cases where the both plates are stationary, right? If you want the flow to move, you have to give the flow some external pressure drop. Okay, you have to give them some pressure force, external explicitly to force flow to move, right? For the flow, uh, if the case is that the one plate is moving, then it is not necessary you have to give external pressure drop to force the flow to move, because that the top plate is already moving, and because the viscous force, it will create a shear layer and drag the flow behind it to moving. Okay, so this is the things. And to solve the flow field, right? When we see we only focusing on the fully developed region. Okay, for the entrance region, it's out of the scope of this class, so we're only focusing on the fully developed region. And to determine the flow velocity profile, right? Because our purpose is that we want to solve that what is the v velocity profile as a function, on the y direction as a function y, in the fully developed. Okay, what that profile will be. And we have two methods to do that. The first method is that we just try to solve the full Navier-Stokes equation. Okay, and we may make some simplification. We can make some simplification on that Navier-Stokes equation based on our assumption of fully developed, because that we know that for the fully developed, u is only a function of y, not a function of x. So based on this assumption, you can simplify the Navier-Stokes equation a bit, and also that the flow is a steady state. Okay, transient, the transient term can gone. We assume incompressible. You can take the rho outside of the those the differential operators and so on. Okay, this is the one method we can do, but we didn't using this way. Okay, and the textbook following another method. Basically, we try to study the x direction momentum on a differential. Let me show you to that slide. Actually, we try to do a x direction momentum equation to study a differential control volume inside the flow field. Okay, we try to see that what's the pressure force, what's on the left and right, and what is the viscous stress force on the top and bottom, right? And based on what we find, we get a differential equation for the top. And the momentum equation basically, you know, it's turn out that it's just basically saying that the f direction, the x direction, the surface force summation is 0. And based on this, we can, we get the equation for the tau yx, and we know that the tau yx is mu du dy. So substitute this one to it, we obtain a differential equation for velocity. Okay, we integrated on the y twice, we get we can get the velocity profile. The unknown constant inside will be determined by the boundary condition, right? So this is what we did there in the last class. After you got the velocity profile, you can use this profile to calculate it that what is this shear stress at the wall, what is the total volume flow rate, and what is where the maximum velocity will happen. Okay, and this kind of thing. Okay, and all the solutions we got obtained. Okay, this partial p, partial x is inside is in it as a solution. Okay, because why? Because that we prove that this in this cases this partial p, partial x actually is a constant value. Okay, and also we mentioned that if the both the plate is stationary, you will really need to apply some external pressure drop, right, to force it. So usually, if both plate is stationary, this value should be known. Okay, and one important things I want to re-emphasize is that in these cases, it turns out that the maximum velocity point is happen at the middle line, right? The middle line, the center line, and its value will be 1.5 times of the average flow velocity. Okay, so this is for the flow between two stationary plates. Okay, and if we change the boundary condition a bit, we have the second case. Okay, we can change the boundary condition so that make the top plate moving with a constant velocity u. Okay, and so in these cases, we just follow the same idea. Okay, try to get the x direction momentum equation on that control volume, and we again obtain that f of x equal to 0, the surface force on x direction will be 0. From there, we obtain a differential equation for the tau, and then the differential equation for the u, right? It's basically the same thing there. But the only thing changed with the stationary plate cases is that the top boundary condition is changed. So, and because the boundary condition is changed, that unknown constant value C1 we obtained here is also different than the one we obtained before. So we will have new velocity profile for these cases, and then from this new velocity profile, we can also get the shear stress tau, volume flow rate, and average velocity, and where, and the maximum velocity, and also where this maximum velocity will happen. Okay, so this is what we did in the last lecture. Okay, and here we continue for that. Okay, now we consider the second cases for the internal flow. Is that instead of flows through between two parallel plates, let's consider that flow inside a circular pipe. Okay, so what's the difference with the previous one? One immediately difference you can see is that in the previous one, for the flow between the flat plates, right? Basically, we're using a Cartesian coordinate, right? X, Y. And now, because it's circular pipe, so it will be more convenient that to use a cylindrical coordinate rather than using a Cartesian coordinate. Okay, so we make the flow direction still as X. Okay, but we make the radial direction as R of that cylindrical coordinate. Okay, and because it's a circular pipe, right? So the flow actually is axis symmetry. Okay, so actually we do not need to consider the variation on the theta direction. On the azimuthal direction, actually we can assume that there are no variation on that direction because flow is 330 degree, right? And is symmetry on that direction. Okay, and for that, okay, again, two methods we can solve this problem to try to get the velocity profile. So, we can starting from the Navier-Stokes. Okay, similar idea, as I said before, but we didn't do that in this textbook, and we again, okay, try to solve the problem by applying the x direction momentum. X direction is the flow direction, okay, the flow direction momentum equation on a small control volume for the flow inside. Okay, so this picture showing you that what this control volume looks like. Okay, and also, so if you take this control volume out, we also try to find that what is the pressure surface force on the left, pressure surface force on the right, what's the viscous stress force on top and viscous stress force on bottom. Assume that if we know that this p value, the pressure and tau x at the middle of this this control volume. Okay, so that the left face, the right face, the top face, and the bottom face, their value will be, let's assume that, okay, in this case it's a little bit different than previous one. Okay, let's assume that we know the pressure and the tau on the left and the top, so that the pressure force on the right and the tau value on the bottom actually can be obtained, through the Taylor series. Okay. And another thing you need to realize is that when you convert the pressure stress, the tau stress, to the force, right? You need to multiply the area of this surface, right? And in these cases, okay, on the left and the right side, that area actually is this annulus area. So that's the reason that you need to times this at 2 pi r. 2 pi r is what? 2 pi r is this perimeter. And then times another dr, you get this area of this annulus. So for the left and the right side, what this is will be their surface area. On the top and the bottom, the surface area also changed to 2 pi r times dx. Okay, so you have the stress times the area, get the force, and similarly on the for all the surfaces. Okay, so in summary, okay, if you try to study the x direction momentum equation, I didn't write it in the cylindrical coordinate, but the result you get should be similar as before. Okay, the transient term is gone because it's steady state. Okay, there is no gravity force, so we assume that the gravitational force is not important, so the body force is gone. And also that we assume is fully developed. Fully developed means that the velocity profile is same. You won't change on x direction, so that how much of the momentum flowing from the left will be just equal to how much flow, momentum flow out from the right. So that surface integration for the momentum flux is also gone. So the only thing left is, again, okay, it will be the surface force on the x direction will be 0 for these cases. Okay, so we have these 4 surface force, the left one, the right one, they didn't using the bottom and the top. Okay, this is not accurate in this cylindrical cases. Actually, we call this this is the inner side, the inside the annulus. This is the outer surfaces. Okay, so this Fi and Fo, the inner surface and outer surface of this annulus. So what the forces will be, x direction forces will be. And this Fs x is equal to 0. So basically you add all these 4 terms, it should be equal to 0. Okay, and after when you add it, right, some term will be cancelled out. Okay, so that, for example, this pressure and this pressure is gone. This tau is gone. Okay, so you get this one. And also that if you try to divide that on the both sides with this 2 pi dr dx, 2 pi r, 2 pi dr dx, and you will get this equation here. Okay, is again, okay, if you're taking a look at this equation, okay, the left hand side of this equation is only a function of r. Okay, and on the right hand side equation, it looks like the equation should be only a function of x. Okay, so the function of a function of only r and equal to a function only x, the only possible way is that they are all equal to the same constant. And that's why that again we find that for the flow inside a circular pipe, if the flow is fully developed, their pressure drop should be a constant. So this is part of p, part of x. You can rewrite this part of p, part of x actually as dp dx, and it's just a constant. Okay, so it means that the pressure drop inside this fully divided pipe flow is a linear line. The slope is unchanged. It's constant. Okay, and you rewrite this one because this part of p, part of x is constant, so you can try to integrate it. Okay, on r to get this tau rx. Okay, this is the tau x you get. Just try to integrate on r on the both sides because it's part of p, part of x is constant. And also that this tau rx is given by this Newton's viscosity law with mu equal to mu times du of dr. Substitute into it, okay? And then you get this equation for u. Integrate this equation again on r direction, on radial direction. Okay, we get this final velocity profile we have. Okay, so for this one again, okay, because we integrate on radial direction, right, twice. So we generate two unknown constants, C1 and C2. To determine this C1 and C2, we need the boundary condition. Okay. One boundary condition is very obvious. Okay, is that at R is larger R. This larger R is the radius of this circular pipe. Okay, it's wall. So that means that U will be equal to 0 there for the no slip condition. Okay, so this is the first one. But we also need the second one. So where we can find the second boundary condition? The second one boundary condition is coming from this symmetry behavior. Okay, at R equal to 0, at R equal to 0, that is the center line, right? It's the center line of the flow. And we assume that we know that at the center line of the flow, actually this velocity u should be a finite value. Okay, and then if you're taking a look at this equation here, result you get here. If you put r equal to 0 here, this ln 0 will go to the what? Will go to infinity, minus infinity actually. Ln r, no, it's going to ln r. Oh, what's the profile of ln r? I forget. E this way. Yeah, I think it's go to the minus infinity actually. So that if you keep this term for at r equal to 0, this u will not become a finite value. Okay, so the only possible way is that you have to remove this term. So C1 has to be 0. So from this boundary condition, okay, at r equal to 0, u has to be finite, C1 has to be 0. Okay, and then from the second boundary condition, you substitute into it at r equal to larger r, the radius of pipe, u will be equal to 0 at there. You can find the C2 value. Will be this way. Okay, and with these two unknown constants from these two boundary conditions, we get the fully developed flow velocity profile. Okay, this is only valid for the flow inside a circular pipe for the fully developed flow. Okay. And again, you can see that the flow profile is a parabolic profile on R. Okay. And this part of P, part of X here is the pressure drop, is a constant, as we said, we were already proved. Okay. So from here, okay, from this velocity profile, we can also quickly, similarly to for the flow between the parallel plates, we can using these results, try to calculate the what's the shear stress at the wall. Okay, so tau not only at the wall, everywhere. Okay, tau rx will be mu du dr. You substitute this u result we get into here. Okay, it can telling us that the shear stress will be equal to this value, r over 2 part of p part of x. And also we can calculate the volume flow rate, integrate all the wave velocity on all the dA, and remember this dA will be 2 pi r dr. Okay, for the cylindrical coordinate on the r direction, on the cross-sectional direction. Okay, so this 2 pi r is a parameter times the dr, give you the area. Okay, you substitute u value into it and do the integration, and final result showing you that what the volume flow rate will be. So this is the volume flow rate will be. Okay, and again, because that partial P, partial X is a constant, right? So basically, if we know the pressure drop on the left side and the right side, if we know the pressure as the inlet and outlet of this tube, okay, basically we can assume that this partial P, partial X can be just written as minus delta P over L. The reason is minus is because that to force the flow moving to the right, the left-hand side pressure must be larger than the right-hand side pressure. So when you're using the right-hand side minus the left-hand side, it actually is a negative value. Okay, that's the reason we add this minus sign here. Okay, so because that usually when we try to calculate the delta P, actually is defined as P1 minus P2. Okay, what is P1, P2 is that if you have a tube, right? So this is one at the inlet and this is by 2. But this partial P, partial X actually is what? It's P2 minus P1 over X2 minus X1, right? So actually it's minus delta P over X2 minus L. So that's the reason we have this minus sign here. Okay, because we define delta P as P1 minus P2, not using not that we define delta P as P2 minus P1. Reason is that usually the pressure at the inlet. Reason is that pressure at the inlet must be larger than the pressure at the outlet, so that it forces the flow to move right. Okay. So by doing this way, we can also that get this volume flow rate instead of using partial P, partial X as the delta P and L. So this equation telling us what? So basically, this equation telling us that if flow is fully developed, actually we can using the volume flow rate, using the pressure drop to try to calculate the viscosity mu. You know what I'm talking? So is that because Q equal to this value, and this pi, this is D, this L, this pi, this D, this L, right? This is the diameter of the tube. This is the length of the tube, right? So this is geometry. The tube is fixed. And if I can measure the, if I given a delta P on the left and right hand side, and if I can measure the Q volume flow rate, I can calculate what the viscosity of the mu of the flow. So we have one example problem for this. Okay. And with this velocity we have velocity profile we have, you have this Q, you divide it by the area, what's the area, pi r square, right? So you're using this Q divided pi r square, you can get the average velocity. So it's showing you that this is with the average velocity. Okay, and if we want to find that where the velocity has maximum value, right? Because the velocity is a function of r, right? And you just do this dOdr equal to make this dOdr equal to 0. You substitute the u profile you get into it. It will return to this result, and make this to 0. So it's telling us that r has to be equal to 0. So it's telling us that the maximum velocity happens at the center line. Okay, you substitute r equal to 0. You substitute r equal to 0 here, make r equal to 0, you get the maximum velocity. The maximum velocity will be this value, minus r squared over 4 mu partial P partial X. So this is the maximum velocity you have. And if you compare this maximum velocity with this average velocity, what do you find? So the only difference is that this average velocity is r squared over 80 mu, right? And this is the r squared over 4 mu. So this maximum velocity actually is twice of the average velocity. Okay, so if you look this profile, velocity profile for fully developed flow, fully developed laminar flow, okay, you will see that, this is the profile, okay, and the error inside will give you, because density is constant, right, the error inside will give you the volume flow rate, right, and this volume flow rate, and actually from there you can calculate an average velocity, okay. The average velocity is just like that you draw this black dashed line here, okay, so that the area between this solid line, this dashed line will be just equal to the area below this real velocity profile, okay. So this will be average velocity, and this line here, this velocity here, will be just 1/2 of this maximum velocity, okay. So the average velocity is happening in the middle here. So this is the maximum velocity, right? This is where the r equal to 0. Okay, so this is where the maximum velocity. So average velocity is only half of the maximum velocity. So this is for the velocity profile of fully developed flow, laminar flow inside a circular tube, circular pipe. Okay, so this is a very important result we got here. Okay, and also this result is different with what we find in the for the flow between parallel plates. So what's the result we get for the flow of parallel plates? Let's go back. So this is the flow we get for the parallel plates. So if the two plates are stationary, so the maximum velocity is not twice of the average, okay? It's 3/2. Yeah, another word, okay? For the flow between the two parallel plates, so if this is the flow profile, and this is the maximum velocity here, and the average velocity will be where? Will be here. 2 of 3 of the V of max will be V of average, right? Because from here you know it. So this is for the flow over between the two flat plates, okay? So we have different result, right? Between the two between two parallel plates, V average is 2/3 of the Vmax. For the flow be inside a circular tube, V average is half of the Vmax. V average will be half of the Vmax, right? So V average is half of Vmax, Umax, okay? And if we using this Umax, to represent this flow profile, right? So basically, you can write that this U over Umax will be 1 minus R over R squared. Okay, so this is a parabolic profile we're showing you here. Okay, so keep this in your mind. And so this is the solution, for again. Okay, let me emphasize this one more time. All the results we get here, we have a restriction for it when you can use it, right? It must be first, must be laminar flow. Okay, it cannot be turbulent flow. Second, it must be fully developed. Okay, on the entrance region, you do not have this. And third, it's the only flow inside a circular tube. If it's a flow not on circular tube, it's rectangular tube, or flow like not be inside the tube, like flow between the parallel plates, or those kind of things, you won't be able to use the result we got here. Okay, and also you need to understand what the meaning of the fully developed. Fully developed means what? Means that this velocity profile is only function for R, will not change on this x direction. Okay, so this is another result we get for the internal viscous flow. Okay, for the flow, fully developed flow inside the circular tubes. And actually, this case has more application importance than the previous cases. Okay, because that in the realistic engineering cases, the flow inside the tubes is more commonly to see. Okay, so keep this in mind. And we have an example problem to demonstrate you, because from here I showing you. I remember that when we get this flow rate as this result, actually, if we have some equipment, right? If we can measure the Q and measure if we know the delta P, we can use this equation to calculate the mu viscosity. So this is an example problem to show you that. Okay, so this equipment we call the viscometer. So basically, it allow us to measure, measure the viscosity of the flow. Okay, so the way they measure the viscosity is exactly using this equation here. Okay, and we try to get the in the flow. Okay, where the flow is fully developed, we try to measure that what is the volume flow rate. Okay, and also that we also try to get the pressure drop. Okay, and from this equation we can calculate the mu. Okay, so in this problem, okay, we know that the diameter tube is given, the tube length is given, the pressure drop delta P is given, and also the volume flow rate is given. So everything is given. We just need to use this equation to calculate mu directly. Okay, so this is how we calculate the mu results. It's telling us that in this problem, this viscometer basically will measure the flow viscosity at this value. Okay, and again, okay, after you get this one, we need to make sure that the flow is laminar, right, not turbulent, because if it's turbulent, we cannot use that equation. So we can also using the Q to calculate what's the average velocity, and using this average velocity to define the Reynolds number. And we see that this Reynolds number basically is smaller than 2300. So we know that it's laminar flow. Okay, so this is 2300. So it's not the same value we had before. Okay, for the flow over flat plate. Let me have another example problem. Okay, so this is for the flow for the parallel plate, right? We have an example before, right? So this is this one here. So another thing I forgot to mention in the last class is that to determine the flow, whether or not the flow is laminar or turbulence, right? We compare with the critical number, right? So this 3000 is for the circular tube. Okay, for the flow between, this is for the flat between parallel plates. So they are different value. Okay, I didn't make it clear, so let me emphasize. So this Reynolds number critical is 1400. We're using the example 8.1. This is the critical number for the parallel flow between parallel plates. And this critical number 2300 is for the circular tubes. Okay, so I didn't, in the last class, I didn't make this very clear, okay? But now I just want to let you, notice this. And that's why that, here, in this example problem, actually they are comparing with 1400, not comparing with 2300, okay? And in this problem, you see that it's actually compare with 2300. Okay, and keep this in mind. So here we, we get the flow result. Okay, the velocity profiles and so on, those kind of all the other quantities. Okay, for both the flow between the parallel plates and for the flow inside the circular tubes. And what is happen if the tube is not a circular tube? Like if you have a rectangular ducts. Okay, how you can do that? Okay, the textbook do not have a section to illustrate that, but the ideal case, in the engineering, what we did is that we have a concept. Okay, so this part is not included and not required for the exam. Okay, in the engineering, what we do is that we include a concept called the hydraulic diameter, DH. Okay, so DH is equal to 4A over S. 4A over P. Sorry, I made a mistake. 4A over P. So the A is the cross-sectional area of the duct. P is the parameter, the weighted parameter of the duct, and times 4. So that so it's a concept, basic concept of this hydraulic diameter is that if you have a rectangular tube or triangular tube or whatever, okay, you calculate their cross-sectional area for the A. You calculate their weighted parameter. Okay, the parameter must be weighted, means that the flow is contacted with it. Calculate P, so you can calculate new diameter DH, so that we can knowing that okay, so the flow problem for this one will be equivalent to a circular tube problem with a DH, so that you can still using the equation we developed for this Q, those kind of thing, right? So not Q, for the tau, those kind of thing. We will have it will be close, okay? We will not exactly same, but on the engineering, the error can be neglected. So that's why we have this so-called hydraulic diameter for the non-circular tubes. Okay, that's some introduction for you. And another thing is I want to mention is that for the flow, right? Because that you know that for this flow inside the tube, and because this no slip condition at the wall, right? So basically we have the friction at the wall. This is tau of Rx at R equals 0, right? It's tau of wall, right? So basically that we have a friction between the fluid and the wall. And is this friction, okay, giving us the pressure drop? Why? Because that from our axial momentum equation. Where is it? Yeah. Okay. Because that from our not here. I'm doing. Because from our axial momentum, right? We are seeing that you know, this pressure drop actually will just equal is given. We need to the pressure drop need to balance with this friction force. Okay, and in the engineering problem, okay, in the realistic engineering problem, what we want to do is most times that we want to reduce this pressure drop, right? Because that the higher the pressure drop means that we need a more powerful pump to, you know, to maintain the flow rate. Okay, so that is why is that when we create the when you try to filter out later on, right? If you in a company you want to buy some equipment, you want to buy some pipes, right? For the flow for the flow inside. One of the big parameter you want to, the first big parameter you want to, you know, consider you know, investigate is that you know, how much of the pressure drop for that pipe will give you, right? Because that if it's a larger pressure drop, okay, when you're using that, when you buy that equipment, you may need to cost you a lot, okay, for the electricity pump you need to use for the pump. Okay, and how we calculate that pressure drop is measure that pressure drop. Okay, it's definitely determined because that this is the friction between the pipe wall and the fluid, right? It's definitely determined by the wall conditions, right? If this pipe, if this is pipe, right? If this inside wall is very smooth, not very roughness, not very rough, okay, the roughness is small, then definitely we know that the delta P will usually be small. That the pressure drop will not that big, right? But if this pipe is very rough, because that this pressure drop is not only determined by the it's you know what we learned here, okay, what we learned in this class, you know, is we assume that this surface is always smooth, okay. That's why is that you know, delta P is only determined by you know, this tau W is only determined by mu du dy, okay. It looks like it's only determined by the fluid viscosity and so on, right? You know what I'm talking. And but in the realistic problem, actually your surface is not that smooth. Okay, this roughness also bring you a lot of pressure drop. Okay, so basically the real pressure drop will contain both this viscous stress at the wall plus an additional friction at the wall due to the surface condition. Okay, and so that's I want to let you know this. Okay, so the limitation. This is the limitation of the things like the result we get for the previous one. We assume that this tube is fully smooth. Okay, and in the real case it's not that. And regarding to the pressure drop, the pressure drop will definitely, then the pressure drop, because based on what I introduced, right, it will including several components. One component is from this one. One component is from the pressure drop we obtained before, right? Due to the viscous force on the, even the tube is smooth, we still have that pressure drop. And other components like the roughness component and so on. Okay, for the component, for the first component, where due to the viscosity of the flow, even if the tube is smooth, we can define a new parameter called the friction factor, F, to calculate the pressure drop. Okay, so this friction factor F is defined in this way. Okay, so delta P for the flow. Okay, if you have the flow, So this if this flow has length L, so delta P will be, so this is P1, this is P2, right? Delta P will be P1 minus P2, okay? Delta P will be equal to F of this friction factor times this length L and times this diameter D of the tube, divided by diameter D of tube, and times the rho V average square over 2. Rho is the fluid density and V average is the average fluid velocity. Okay, so by this way, we can define this F friction factor. Okay, and based on, so this is definition of the friction factor. Okay, based on the result we obtained before for fully developed flow, we already know that this is the U profile is equal to this one, right? The velocity, the maximum velocity will be actually equal to this value, will be 2 times the average velocity. So this average velocity will be this r squared over 8 mu part p part x. And actually this part p part x, because of that we know is constant for the fully developed flow, it can be rewritten as this delta p over L. Actually it's minus delta p over L, so that you can cancel this minus sign, okay? So if you substitute this part p part x with this minus delta p over L, okay, and then you replace this average for the things here into here, you can prove that for the laminar flow, fully developed, okay, fully developed laminar flow, okay, in a circular tube, actually it's showing you that this F value will be 64 over real number. Why we got 64? You know, maybe we should try to do this together, okay? So this delta P over L it will be F over D times this rho over 2 times this V average square, right? So this V average square will be minus R square over 8 mu. This part of P part X, I replace it minus part of P, so I make it this one. Okay, so this one is cancelled. Okay, and what I see, and R square, right? R square is because of R is 1/2 over D, right? So R square will be 1/4 D square, right? So you change this R square to D square and make it this here will become 32, and 2 times 32 will be 64, right? So this will give you that you know, F will be 64 on to make it to the right, and you have mu, you have this mu here, you have mu on the, you also have the mu on the bottom, and you have this rho, you have this V average. We also have V average here. I forgot to add it. We need to add. We need to left the V average. We do not need to. So anyway, so in the end, you get this 64 here. So it's showing you that this laminar flow, it will give you the friction factor will be 64 over reasonable number for this fully developed circular tube. Okay, so why we need this, right? So this factor is very useful, okay? Because that if we have a circular tube fully developed, we can quickly calculate what's the Reynolds number first, and then using this equation we can calculate this F value. And after we know the F value, we substitute into this equation. We know the F value as function Reynolds number 64 divided by for fully developed flow, and we know the length of the tube, we know the diameter of the tube, we know the average flow rate. Because usually we know the mass flow rate, right? So or volume flow rate, so we can know this V average. So substitute things inside, you can quickly calculate what the pressure drop will be. Okay, so it's just a different definition. Okay, so basically what I want to say is that instead, you know, instead using this result we obtained before, you can using this F factor with these correlations to calculate the pressure drop for the flow inside the tube. Okay, so this is new, another concept I want to introduce. Okay, and the last topic of this chapter is for I want to give you some basic introduction to the turbulent flow inside the tubes. Okay, All we talked about before is for the laminar flow. And what will looks like if the Reynolds number is very large. Okay, for the circular tube, for example, if the Reynolds number is larger than 2300, we know the flow will become turbulent, right? So all the things we got before, it won't valid anymore. So for the turbulent flow, how we get the result? Okay, two ways, analytical or experimental. Analytical is very difficult for turbulent flow. Okay, because that for the turbulent flow I introduced before, right? It will have some random behavior, so that which means that the statistic things, okay, so those possibility functions things will be involved when you try to write the flow equations. Okay, so make the math very hard to solve. Actually, and also that for another difficulty for the turbulence is that actually turbulence flow, these turbulent things inside, we call the small eddies inside the turbulence. Actually, they will also, as a behavior, try to dissipate the kinetic energy, the flow energy, into the thermal energy. Okay, so actually, it's not like the laminar flow that after the flow is, for example, flow is fully developed. Okay, their kinetic energy will not change. No, for the turbulence, it's not. It keep losing the energy to convert it to the to the internal energy. Okay, and so the things are very difficult. Even the fundamental basics for the turbulence these days, nowadays, okay, is not the scientists will not say that they fully understand it 100%. Okay, so it makes the analytical solution very, very difficult. And with some help of a supercomputer, it's possible, to solve this numerically. Okay, but it also will become very expensive if the problem is also very, the flow geometry is also very complicated. Okay, so that makes the, in the engineering side, okay, our engineering side, we focus on the application, right? So that makes the empirical study for the turbulence very useful. Okay, and that is why that for the turbulent flow, we have a lot of empirical correlations, can quickly giving us that, from the previous experimental data, we try to do some regression. Okay, on those experiment data, we see that what things will look like for the turbulent flow. Okay, and one thing I also want to let you know is that the velocity profile in the turbulent flow is also different for the velocity profile in the laminar flow. Okay, so this picture showing you what it looks like. For the laminar flow, this is the velocity profile. And for the fully developed turbulent flow, this profile becoming something like this. You will see that actually the maximum velocity will be reduced. Okay, so that, this is very steep. This slope is very steep, right? But the slope here is not that steep here. But instead, you will have very steep slope at the close to the wall. Okay, remember between these two profiles, right? The area inside must be same. Assume that the area inside is up, because the area gives us the volume flow rate. Let's assume that the volume flow rate for this laminar and turbulent is the same. Okay, so the area inside should be same, but this one is very steep, and this one is not that steep. So which means that for the turbulent flow, right, you have a large region that the flow velocity will very close to its maximum velocity, but this maximum velocity will be smaller than the laminar flow max velocity. And also that so that this will result in that because this is still no slip condition at the wall, so this will result in that in a very short range, in a very small range, this velocity we need to increase to a large value. So what does this mean? This means that the velocity gradient at the wall for the turbulent flow is usually larger, is larger than the velocity gradient for the laminar case. So what does that mean? Because tau yx equal to this one, right? Tau of wall, okay, at y equal to 0. So what does that mean? That means that because this slope here, this du dy is larger than here, so usually the wall shear stress at the wall is much larger in the turbulent flow than in the laminar flow. So in another word, for the flow, turbulent flow inside the pipe, you will have larger pressure drop due to the friction comparing to the laminar flow. Okay, very important result. Pressure drop inside the turbulent flow in a pipe is larger than pressure drop of a laminar flow. Okay, and so this is the things. And also, we also, as I told you earlier, right, for the turbulent flow, we also have a lot of empirical correlations, right? Another empirical correlation I can give you is that for the turbulent flow in a pipe, their entrance length is also different than the result we got before. So the entrance length we had before is LOD is approximate 0.006 Reynolds number, right? This is what we got the entrance length before. What I give you in the beginning of this class. This is for laminar flow. But for the turbulent flow, it's usually LOD just approximately 10. So what that means is it means that if the flow try to go into a pipe, if it is turbulent, so usually like this length is like a 10 diameter of this length, the flow will already become fully developed. And you can find that if you try to, because that the critical value is 2300, right? You substitute 2300 into here, you will see that this value with this 2300 will be much larger than this one, much larger than 10. What does that mean? That means that the entrance length for the laminar flow is much larger than entrance length for the turbulent flow. Okay, so for the turbulent flow, you have a much shorter entrance length. Physically, it's very easy to understand, right? Because turbulent means that you're very chaotic, right? They transport the things faster than the laminar, right? So that's why is that the turbulence means that the viscous force from the wall will much easy, the viscous effects from the wall, right? It's much easier to transport in the turbulent flow. So that makes the flow very quickly become everywhere become viscous, right? So that inviscid curve will be disappear very quickly. And then that's why we're seeing that for the turbulent flow, the entrance length is much shorter. Okay, and the other things, right? Remember that another correlation example I can give to you is that, so this is for the laminar flow, right? I told you that this friction factor is 64 over Reynolds number. So this is, we get this from the from the exact solution, right? Analytical result, this is what we got. And for the turbulence, we have, the different scientists, right? They can do different experimental study. So this is the one result they published in the paper for the turbulence. For the turbulent flow, the friction factor can be given like this. This is one result. This is the Pareto correlation. We have a bunch of, if you go to the literature, okay, we have a bunch of this kind of correlation telling you that, okay, what's the friction factor for the flow in a circular tube, or what's the friction factor for the flow if this tube is very small nanotubes, okay, micro tubes, and what if this tube is triangular, what this tube is rectangular, what this is elliptical, those tube shapes, all those kind of things. Okay, we have many papers for this kind of thing, but they are a lot of them are the empirical results. Okay, and this value f is also much larger than this value here, with just with the same Reynolds number, because that we know that the turbulent flow give you more frictions. Okay, so we will not go to the details for the turbulent flow. Okay, so this is the advanced topic here. What I give here is just some introduction. Okay, and just some qualitatively speaking. Okay, let you know that what's the difference between the laminar flow and turbulent flow. Okay, any questions so far, guys? No question? Okay, so no question. Let's move to the last chapter of this class. Here we finish talking about the viscous flow for the internal viscous flow, right? The next chapter we are going to focusing on the external viscous flow. Okay, now the flow is not flow inside the pipes. Okay, flow is flowing outside. Okay, again, okay, in this chapter I will not cover everything on the textbook. Okay, I only cover a portion of it. Okay, I will focusing on a concept called the boundary layer. Okay, and so for flow over for external viscous flow, what it looks like? Okay, so this is a flow over an airfoil, right? Let's assume that the Mach number is small, okay, smaller than 0.3, so the flow is still incompressible, okay, because that we're only focusing on the incompressible flow. So let's assume that the Mach number is smaller than 0.3, so it's still incompressible, okay, density is constant. And what the flow structure it looks like? So this is the flow field will looks like. Some very complicated behavior, you'll see it here, okay? You will see the things. So maybe I should not using this as an example. Let me give you another example, okay? If I have a flow over if I have flow over a cylinder, okay, if it's inviscid flow, so what's the flow streamline looks like? So you will see that the flow streamline will exactly like this way. So this is what the flow streamline looks like. It's like almost a symmetry from the left-hand and right-hand side, right? But if the flow is viscous, you also have the flow over the cylinder, what it looks like, the streamline. So the flow pattern will totally change. Okay, it will not be, it will become something like this. It will become something like this, and you have the wicks here, you have the wicks here, have wicks here, wicks here, wicks here. So this is an example I want to show you that with this viscous effect, okay, the flow pattern will looks very different. So this is for the inviscid, this is for the viscous. Okay, so for this flow over this airfoil, okay, and at the wall, right, because we still have those no slip conditions, so we know that the velocity at the wall will be 0. Okay, and outside, very far away from this airfoil, we call it free stream velocity, this U infinity. Okay, so that we will have a small region close to the wall that the velocity will become from 0 to this U infinity. And this small region close to the wall, we call it the boundary layer. Okay, and this boundary layer, okay, it can also, the flow inside the boundary layer can also be laminar or turbulence. Okay, so this RBL is a laminar boundary layer, and later on for this airfoil, it may be developed to the turbulent boundary layer. Okay, and the boundary layer thickness, this dashed line is we can see that this is showing you, to distinguish the flow into two regions, right? The outside is the free stream, the inside is the boundary layer flow. Okay, and so that it's showing you that the thickness of this boundary layer is also keep changing. Okay, and because this viscous flow, more complicated things will happen at the end. Okay, you will have viscous wick here, and also at some point you will have those flow separation. The flow separation is generated due to the negative pressure gradient on the wall. Okay, which is if you're interested, you will learn this in the aerodynamics class actually. Okay, I just want to show you. So the whole idea of this one is two things. Okay, this picture is two things. The first thing I want to show you is that for the viscous flow around some blunt body. Okay, it will form a very thin layer close to that surface of that solid surface. That the velocity inside that surface will have a large gradient. At the wall will be 0 because no slip condition, and then at the boundary of this boundary layer, it will change it to the change it to the value close to the free stream velocity. Okay, this is called the boundary layer. Okay, this is the first thing I want to let you know. And the second thing I also want to let you know that if the flow is inviscid or if this flow is viscous, your flow pattern will change a lot. Okay, so keep these things in mind. And for the boundary layer problem, for the external viscous flow problem, right? The The most common benchmark problem we use to study is the flow over a flat plate. Okay, so this is the flow over a flat plate. Okay, so assume that the flow, this is the tip on the left-hand side. Okay, let's assume that we have a uniform flow is approaching to this flat plate. So what will happen? You will see that you know, the boundary layer will try to develop at this tip, and with this flow going on, you know, this boundary layer will become thicker. And inside this boundary layer, if you look in the velocity profile, actually at the wall, the velocity will become zero. And then, you know, it will have a large gradient inside, and at the boundary of this boundary layer, it will be close to this u velocity. Okay, so in another word, okay, for the flow over a flat plate, we can separate the flow region into two parts. Okay, the first part is called the boundary layer region. The boundary layer region is where the viscous effect is strong. The viscous effect is strong because we have large gradient, right? Again, okay, this tau equal to mu du dy, right? Although this mu is always mu is not zero for these cases, right? But whether or not you have tau is determined by du dy. Okay, you only have this large du dy, the velocity gradient inside the boundary layer, right? Because outside the u is like a constant, not changing with the y direction. So that's the reason that for outside we call this, you know, inviscid, no, not called, that called the free stream, okay? Inviscid free stream region. And inside, because you have this large velocity gradient, right? From this equation, we know that the tau will not become zero. So the viscous effect is strong. So this is why the inside is the viscous boundary layer, okay? Layer region. So by this way, okay, we separate the flow into two parts. Outside is inviscid flow. Inside the boundary layer is viscous flow. Okay, and with the inside is viscous flow because that we only have the velocity gradient inside the boundary layer. Okay, so this is the first thing. And the second thing you need to realize that the thickness of this boundary layer is not a constant. Okay, as along this plate direction, actually this boundary layer thickness will keep increasing. It also is very easy to understand, you know, because that we know that this inside this boundary layer is where this you know, viscous friction effect, you know, it is, right? So the larger it goes, this effect will more reach to higher, right? Because that the more this viscous things will be transported to the, you know, further region, you know, above this plate. Okay, so the thickness of the velocity boundary layer is also increases in the flow direction, and also, okay, if this your plate is long enough, at some point, this boundary, the flow inside this boundary layer will be transit from the laminar flow to turbulent flow. Okay, so it always starts the boundary layer. Okay, from this plate tip, it always starts as a laminar flow first. Okay, but after this plate, existing some plate length here, it will become turbulent flow. So boundary layer can also be, we also need to distinguish the boundary, which region we want to study, the laminar boundary layer or turbulent boundary layer. It's also different. Why? Because that the velocity profile is also different. The velocity profile inside will be different, looks like. Okay, and how we determine which region is laminar, which region is turbulent? It's determined by a so-called local Reynolds number. Re of x will be rho times this larger u times x divided by mu. Why is it local? because when we define this real number, we are not using the overall length of the plate. We are not using L. We are using the X. So we need to calculate the real number as a function of X. So this is not a constant value. This is a function of X. Real number, because that, so if this is the X direction, right? So this is X0. Okay, let's assume that at this location, where transition, this is X of CR. Okay, so this RE of CR will be rho of U X of CR divided by mu. Okay, so because Reynolds number, local Reynolds number is a function of X, right? So which means that the larger this X value will be, the longer this flow will be, their local Reynolds number will keep increasing until it increases to a critical value. And this critical value given by this critical position, XCR. Okay, and this critical value is 5, 10 times 10 to 5 for the flat plate. Okay, so what does it mean? That means that if you have this laminar flow over flat plate, from this critical number here, this value 5, 10 times 10 to the power 5, you can calculate what this critical XCR value position will be. So you knowing that on the left side of this XCR will be the laminar boundary layer, on the right side of this XCR will be turbulent boundary layer. Okay, so this is how we determine that whether or not flow is laminar or turbulence. Okay, just keep, be careful about this one, right? Remember that this Reynolds number we use to determine the whether or not flow is laminar or turbulent. We're using a local Reynolds number. This is different the way we did in the internal flow. For the internal flow, we're using that RE of D, right, equal to rho U D over mu. For the flow inside the pipe, we're using the pipe diameter. So this is not a function of X. This is just give you a constant value, right? It's because the D is not D is a constant given. Okay, so this is a global quantity. Okay, this is local quantity. So just be careful this kind of thing. So this is so here I try to give you that what the fundamental flow structure looks like for the flow over flat plate. Two things. Again, okay, let's summarize. The flow will be separated by two regions by the boundary layer. Okay, inside the boundary layer is viscous flow region. Outside the boundary layer is inviscid flow. This is the first thing. The second thing, the boundary layer itself, their thickness will keep increasing on the flow direction. And until it reaches to some critical value XCR, it will be transit from the laminar flow to turbulent flow. And this XCR is calculated by this critical local Reynolds number, which will be equal to 5 times 10 to the power 5. Okay, so this is the thing that I've tried to summarize here. And then the next thing is that how we can determine the boundary layer thickness, right? Because that we're seeing that this boundary layer, right? Is this dashed line to distinguish the flow, right? We want to know that what this dashed line what the y value of this dashed line will be. So in another word, what the thickness of this boundary layer will be. How we know that? So this will require us to give a definition of this boundary layer thickness, right? How we define this at which region? So at which region, the flow, at which position, okay, will be to distinguish between the flow inside the boundary layer or outside the boundary layer, right? How we define that? We have different way to define it, okay, but the most popular way is these three ways, okay. The most common way we define is called the disturbance thickness. Disturbance thickness, or in most time we just call it boundary layer thickness delta directly, okay. But it will define based on the velocity profile, because that we are already seeing that we only have the velocity gradient inside the boundary layer, right? Outside of the boundary layer, velocity will become this big U already. So what we did is that because that this change, right? This U velocity change to approach to this big U is a asymptotic behavior. Okay, we cannot really find a location that at which location this U will become larger U. Okay, so what we did is that we try to define this thickness delta, so that at this delta, this U, small u, will become 0.99, 99% of the larger U, the free stream U. You know what I'm talking? So the first definition of the boundary layer thickness is which we call this difference thickness, is that we're just using the velocity profile to define it. The velocity profile of this flow, so that delta is defined as the distance y from the surface at which u will be 0.99 larger u. So in other words, if we write this in a math equation, it will be u at y equal to delta. So you assume this is y division over larger u will be 0.99. So this is the most common way we define, where is the boundary layer and where is not boundary layer. Okay, so this is the most simple way, but we also have other way. Okay, the second way is a little bit more complicated. Okay, and this one is called displacement thickness. So what does this mean? So if you look in this profile here, if you look in this velocity profile here, okay, you can see that maybe using this as an example. Okay, if you look in this velocity profile here, you see that this is because you remember that if we want to calculate the volume flow rate, right? So we need to calculate the area here. So this area gives us what the volume flow rate, right? Because it's U times this A give us volume flow rate. So this is the volume flow rate before it go above this plate is this length. But after it go above this plate, and this is what the volume flow rate looks like, the area inside, U over dy, right? You integrate this small u on this y direction and times the width of this plate. So this will be the area inside. And you will compare these two areas, the profile, this is shaded region, the shaded region here. You see that the area here actually is larger than this one. Why? Because that the profile here, like some small region here is loose. We lose this region. Right? And it's basically telling us that because this viscous effect on the wall, because there's no slip condition, okay, it will try to reduce the overall flow rate. Okay, we try to reduce the overall flow rate. So the things is reduced in this region. This region is where the things is losing. And if we can calculate this region, what is the flow rate in this region, and then using this region, to divide it by this large U, so it will looks like the overall effect is just like it's just like so if we're using the mass flow rate as an quantity to measure, it just looks like we try to increase this plate with the height of this delta star. This delta star is this new definition of this called displacement thing. It just looks like we try to the original this plate position is here. Now we try to move this plate position to a little bit higher on this y direction, so that above here is still the uniform, and this region dashed region, this region here, it should be U here, right? And this area will be just equal to what you lose here. Okay, so in another word, okay, so it's just like this. So we define this distance called the delta star. So this is called like the effect of the boundary layer on the mass flow rate is on the mass flow rate or volume flow rate. It doesn't matter, okay, because this is incompressible flow. They are the same. Okay, so that's the only difference is the rho. Okay, they are the same things. And so the boundary layer, okay, the effect of this boundary layer for the flow rate is just like we try to make a displacement on this flat plate to move it up with this distance delta star, because it try to reduce the mass flow rate. Okay, and how we calculate this delta star? So if we have no boundary layer, right? So the overall mass flow rate will be this one, rho times u dy over w. This w is the width of plate on this perpendicular direction to the screen. Okay. So if you want to calculate the mass flow rate at this position for overall mass flow rate, you just integrate it on the overall this large u from this y equal to 0 to y infinity, and times this w. Okay, so we got this one. So this is the mass flux if we have no boundary layer. But the actual, because we have the boundary layer, right? So what's the mass flow rate? It will be integrated from 0 to infinity from rho times small u times dy w. You cannot use large u, but you have to use smaller u. Right? This smaller u is this one. You have to integrate instead integrating on this curve. You have to integrate on this curve. Okay, instead integrating on this curve. And what's the difference between them? So using this one minus this one will give you the loss of the mass flow rate due to the boundary layer, right? So you'll be rho times large u minus u times dy over w. And we can imagine that if we're keeping the velocity at a constant u, and instead we move this plate up with the distance delta star. We move this plate up with the delta star, and what is losing here will be this rho times u times delta star times w will be just equal to what is losing here. What is losing here. And by this way, we give the definition of this displacement thickness delta star. Okay, so delta star in the end will be integration from 0 to infinity. Just do the math manipulation on this one. We will give you this 0 to infinity 1 minus small u over large u times dy. Smaller u is the realistic velocity profile, including the boundary layer region. Okay, and if we if we assume that if this smaller u, if we assume that this from what we definition with this delta, from this delta here and there, we know that at y equal to delta, actually this smaller u is already 0.99. So we can assume that instead of integrate from the 0 to infinity, we really only need to integrate from the 0 to delta, because that if the u is if y is larger than delta, this u is more than 99% of this larger u, right? So 1 minus this will be close to 1 already. So we really do not need to integrate it until to infinity. We only need to integrate from 0 to delta. So that's why we have approximate, because that delta is 0.99 u, is not like a 1.0 u. Okay, we lose some accuracy here, and this will be the result. So this gives you the correlation between the disturbance thickness with this displacement thickness. So this is the second definition for the boundary layer thickness. We call it displacement theta. And the last one, theta. And this is called the momentum thickness. So what is the difference? The difference is that when we define this displacement thickness, right, we are basically saying that because the existing this boundary layer, actually we lose some mass flow rate, right? Because u is not this smaller u here is not this larger u. Okay. Now in the same thing, right? If we do not using view this problem from the mass flow rate point of mass flow rate, instead we try to view this problem in the point of view of momentum equation. Okay, because this u is smaller than large u, we also lose the momentum here. Right? We also lose the momentum. So it looks like the problem is like with this boundary layer, it looks like we can also try to move this plate up with another distance theta, so that the loss of the momentum in this region will be equal to the same momentum you lose, you remove here. Okay, so this theta we call is the momentum thickness. And the way to calculate it is same idea. Okay, so without the plate, this will be the momentum, the overall momentum. With the plate, this will be the momentum. With the plate, with the boundary layer, this is will be the realistic momentum. So the difference between the without plate or without boundary layer and with boundary layer, the difference is this one. And you want to make this one will be equal to you remove on this theta, rho times large u square theta. So this rho times large u square theta will be equal to what is reduced the momentum, will be equal to this value. And you try to rewrite this one, you get the definition of this momentum thickness theta will be equal to this way. Okay, the only difference between this delta star is that you have an additional coefficient on the top. You might over for it from 0 to infinity, and then again, okay, you know, we can approximately, you know, just integrate from 0 to delta, because at delta, if y is larger than delta, u is very close to larger u, so this term will become 0, okay, close to 0. So you can also integrate only from 0 to delta. You get this one. So now we define all three definition how we define the boundary layer thickness. Okay, so we have that the first one, where velocity just call the disturbance thickness, or just call the boundary layer thickness based on profile. Velocity is 0.99 of big U. The second one, displacement thickness based on that how much of the mass flow rate is reduced. The third one, momentum thickness theta is determined by how much of the momentum is, you know, reduced due to the boundary layer. Okay, and I will finish here. And in the next Monday, which will be our last lecture, so I will try to finish this boundary layer problems. So right now we will only give you the definition, right? The boundary layer, the concept of the boundary layer was the definition of the boundary layer thickness, and we still do not know that what the thickness this delta really will be, and what the velocity profile looks like, right? And the next class is we will try to solve the fluid equations, try to see that what's the solution for this boundary layer problem. And then we finish the whole class. Okay, I will finish here. Any questions, guys? Anyone? So no question. I will see you guys on Monday. All right. Goodbye, everyone.
Have a good day, Professor.
Enjoy your weekend, Professor.
Bye, everyone. Bye.